In this lecture, I am going to present what is fixed beam and what are the different step-by-step procedures to solve the fixed beam by moment area method. Then I would like to explain the fixed and moments for different types of loading. Then I am going to solve a problem on the fixed beam with UDL throughout the span and central point load. First, coming to what is fixed beam. When both ends of a beam are constrained from both rotation and translation by supports, such a structure is called a fixed beam or a constrained beam. A fixed beam is also called a built-in beam or encastre beam. In a fixed beam, both slope and deflection are 0 at the ends. This is the fixed beam, and this is the support A and support B, and this is the length of the beam. Here both ends A and B are fixed. Then what is the difference between the simply supported beam and fixed beam? So look at this figure. So this is the simply supported beam and this is the fixed beam. So in the case of simply supported beam, there is having the end slopes theta A and theta B. But in the case of fixed beam, the end slopes, that is at A and B, are equal to 0. That is theta A is equal to 0 and theta B is equal to 0. So this is the figure 1, simply supported beam carrying an external load system. At the beam bends, slopes theta A, theta B will occur at the ends A and B. If the end slopes be prevented, it is necessary to apply the end couples or end moments of certain definite magnitude in the appropriate order. When the end of the beams are built in, such end moments are automatically developed. Such moments are called the fixed end moments. So this is the fixed beam. So this is the vertical loading, and due to this vertical loading, so this is the vertical reaction at the both end RA and RB. At the end A, the fixed end moment MA, and at the end B, the fixed end moment MB. Here the slope, so when we will draw a tangent at support A, so the tangent will pass through the axis of the beam. So here the slope is 0 and deflection is also 0. And at B also, if you draw a tangent, that will pass through the axis of the beam. Here also the slope 0 and deflection 0. Then for a fixed beam with inclined loading, there are 6 unknown reaction components. 2 vertical reactions at both ends, 2 horizontal reactions at both ends, and 2 moments at both ends. But there are 3 static equilibrium equations are available to determine the unknown reaction components. So in this case, the degree of static indeterminacy is equal to 3. The degree of static indeterminacy ds is equal to r minus 3. So the total number of reaction components are equal to 6, and the number of static equilibrium equations available 3. So ds is equal to 6 minus 3, that is equal to 3. But for a fixed beam with vertical loading, so there are 4 unknown reaction components, 2 vertical reactions and 2 moments. In this case, 2 static equilibrium equations are available to determine the unknown reaction components. Therefore, the degree of static indeterminacy is equal to 2. In this case, if the loading is vertical, the degree of static indeterminacy is equal to r minus 2. The r is equal to the 4, that is the total number of reaction components, and 2 is the total number of static equilibrium equations available. So ds is equal to r minus 2. So r is equal to 4 minus 2. So ds is equal to 2. In this case, the degree of static indeterminacy is equal to 2. but fixed beam is a kinematically determinate beam. The degree of kinematic indeterminacy is equal to 0. There is no displacement takes place at both ends of the beam. So the degree of freedom or degree of kinematic indeterminacy of fixed beam is equal to 0. Then coming to what are the different step-by-step procedures to solve the fixed beam. Let MA and MB be the fixed end moments. The beam may be analyzed in the following stage. So first consider the beam as simply supported condition and draw the free bending moment diagram due to external loading. Then due to the effect of end couples MA and MB alone, draw the fixed bending moment diagram. Then determine the fixed end moments at A and B, that is MA and MB, using the moment area method. There are two moment area theorem. The first theorem, that is the total area of the free and fixed bending moment is equal to 0. And the second theorem, that is the total moment of the area of free and fixed bending moment diagram is 0. That is A1 plus A2 is equal to 0. Then A1 x1 bar plus A2 x2 bar is equal to 0. Then by using these two moment area theorem, you can find out the unknown fixed end moments at both ends of the fixed beam. Then after knowing the end moments, then you can draw the final bending moment diagram. So already you know what is the simply supported bending moment diagram. After knowing the fixed end moments, then you can draw the final bending moment diagram by combining the simply supported BMD and fixed BMD. Then by taking both external loads and fixed moments at the ends, determine the reaction for the fixed beam. Then determine the shear force value and draw the shear force diagram. Also find out the point of contraflexion. So here assuming the free bending moment diagram is positive and fixed bending moment diagram is negative. So the area of free BMD, that is equal to the area of fixed BMD. Similarly, the moment of area of free BMD from A is equal to the moment of area of fixed BMD from the same end A. That is A1 x1 bar is equal to A2 x2 bar. So by using these two moment area theorem, you can find out the fixed end moments. So these are the procedures. So you have to apply to find out the fixed end moments. Then you can draw the bending moment diagram and shear force diagram. Then you can find out the point of contraflexion. Then you can find out also the maximum bending moment position. Then coming to what are the fixed end moments for different types of loading. These are the sum of the fixed end moments for different types of loading is summarized in a tabular form. So this is the fixed beams and this is the fixed moment at end A, this is fixed moment at end B. So this is the fixed beam of length L and the W is the concentrated load which is present at the midpoint of the beam. So in this case, the fixed end moment at end A is equal to minus WL by 8. Similarly, the fixed end moment at end B is equal to minus WL by 8. MA is equal to minus WL by 8 and MB is equal to minus WL by 8. And the slope and deflection at the end is 0. This is the fixed beam of length L and here having the uniform distributed load throughout the span, that is W per unit turn. So here the fixed end moment at the end A, MA is equal to minus WL square by 12 and the fixed end moment at the end B, MB is equal to minus WL square by 12. And this is the fixed beam of length L and here having the load W at a distance A from the support A and B from the support B. So this case, this is the eccentrical loading. So here the load is present eccentrically. So this case, the piston moment ma is equal to minus WAB square by L square, and MB is equal to minus W square B by L square. Similarly, so this is the fixed beam and the length of the beam is L, and here this is the varying loading. This is the varying loading, and here the load is 0, and at B the load is W per unit length. So this case, the piston moment at end A, MA is equal to minus WL square by 30, and MB is equal to minus WL square by 20. And this is the fixed beam, and here the length of the beam is L, and here the load, total load W. This is the total load W. This is the triangular load, and the length of the beam is L. So this case, the piston moment at end A is equal to minus 5WL by 48, and MB is equal to minus 5WL by 48. So this is the fixed beam of length L. Here the moment is present at a distance small a from the support A and small b from the support B. So this case, you have to take the piston moment MA is equal to minus M small a by L square into 2b minus a, and MB is equal to minus M into small b by L square into b minus 2a. So these are the piston moments that you have to take during the analysis of fixed beam. Then coming to the first example, a fixed beam of 4 meter span is carrying a UDL of 10 kilonewton by meter over the entire span, and a point load of 10 kilonewton at the mid span. Draw the shear force diagram and bending moment diagram, and EI is given 2500 kilonewton meter square. The length of the beam is given 4 meter, and this is end A fixed and end B fixed, and here having the UDL throughout the span of intensity 10 kilonewton by meter, and also having one concentrated load at the midpoint of the beam, that is 10 kilonewton, and you have to find out what is the piston moments MA and MB, and you have to draw the bending moment diagram and shear force diagram. Figure 1a shows a fixed beam AB of span 4 meter carrying a point load 10 kilonewton at midpoint and UDL 10 kilonewton by meter throughout the span. Here you see, due to the symmetry of the loading, the moment at the end A and moment at the end B both are equal. So MA is equal to MB is equal to M. Both ends the moments are equal. First you have to consider the beam as simply supported condition. Then you have to draw the free bending moment diagram due to external loading. So this is the fixed beam, and first you have to take the simply supported condition. So this is the simply supported condition. So in simply supported condition, you have to take only the UDL and point load. What is the load is given on the beam, that you have to consider, and you have to find out what is the end reactions at both ends R and RB. Then you have to draw the free bending moment diagram. First you have to take the beam with simply supported condition. You have to take only the load, and you have to find out reaction. Then you have to find out the moment at different points. Then you have to draw the free bending moment diagram. Then you have to take the end couples. You don't know what is the end couples, what is the end moments, that you don't know M and MB. So that you have to find out. Here you have to find out directly the M and MB by using the formula. So what is the moment at the end of the beam if the UDL present throughout the length? Similarly, you know what is the moment at the end of the beam if the point load is present at the midpoint. So by using that formula, you can find out directly what is the end moments. Then after knowing the end moments, then you can draw the fixed bending moment diagram. This is the fixed bending moment diagram. And after plotting the fixed bending moment diagram, by combining the free bending moment diagram and fixed bending moment diagram, so you can draw the combined bending moment diagram. So first coming to the free bending moment diagram, this is the figure. So from this figure you can find out first the reaction, what is the reaction at the end A and at the end B. So the reaction at the end A you can find out, or the reaction at the B you can find out by taking the moment from the other ends. If you want to find out the reaction RB, so you have to take the moment about the support A, then you can find out what is the reaction at B. For RB, so here you take the moment about A. RB into 4 meter, this is anti-clockwise, and due to this load, the moment is clockwise. Due to the point load or the midpoint, the moment at the end A, that is equal to 10 into 2, and due to UDL, the moment at the end A is equal to 10 into 4 into 2. But these two moments are clockwise, so this is negative, and this moment is positive, RB into 4. Here the load is present, symmetrical loading. So you can also find out the reaction by taking the symmetrical loading. So here the load is given symmetrical, so you can find out the reaction at both ends by taking what is the total load is coming on the beam. So the total load divided by 2, that is equal to the reaction at A and reaction at B. So from symmetry of loading, RA is equal to RB is equal to half into total load. So half into the total load, 10 into 4 plus 10. So this is equal to 25 kilonewton. The reaction at both ends are equal to 25 kilonewton. Then you can find out the free bending moment at different position. So what is the free bending moment at A, and what is the free bending moment at C, and what is the free bending moment at B. At A the free bending moment is equal to 0, and at C what is the free bending moment? So that is RA into 2 meter, and due to this UDL minus 10 into 2 into 1. RA into L by 2 minus 10 into 2 into 1, that is 25 into 2 minus 10 into 2. So this is equal to 30 kilonewton meter. The free bending moment at C is equal to 30 kilonewton meter. Then what is the free bending moment at B? So at B the free bending moment is equal to 0. You know at the end the bending moment is equal to 0. So the moment at A is 0, and the moment at B is equal to 0, and the moment at C is equal to 30 kilonewton meter. Then after knowing the free bending moment, then you can draw the free bending moment diagram. So this is the free bending moment diagram. So this is parabolic. Then you have to find out what is the piston moments at the end A and what is the piston moments at the end B. You don't know what is the piston moment at the end A and end B. By using the formula, so you can find out what is the piston moment at the end A and B. The fixed bending moment MA is equal to MB. So that you can find out that is due to the central point load and due to the UDL. So here this is the UDL, this is the central point load. So due to these two load, you have to find out what is the moment at the end A and what is the piston moment at the end B. That is MA is equal to MB is equal to fixing moment at support due to central point load only, plus fixing moment at the support due to UDL only. Due to the central point load, so the moment at the end A or moment at the end B is equal to minus WL by 8. And due to the UDL, the moment at the both end is equal to minus WL square by 12. Then you can find out what is the end moments. MA is equal to MB is equal to minus 18.33 kilonewton meter. Then after knowing the piston moment, then you can draw the combined bending moment diagram. So this is the combined bending moment diagram or final bending moment diagram. Here you know the piston moment at end A minus 18.33 and at end B minus 18.33 kilonewton meter. And this is the free bending moment diagram. already you know. So combine these two figures, the free bending moment diagram that you have to take positive and the fixed bending moment diagram that you got the negative value. So here this is the negative bending moment. You have to take the negative bending moment diagram. After combining these two, so this is negative and this is positive and this is negative. This is the combined bending moment or the final bending moment diagram of the fixed beam. So here you have to find out what is the point of contraflexion. This is one point of contraflexion. D point is the point of contraflexion and E point is also the point of contraflexion. So you have to find out these 2 points of contraflexion. So due to symmetrical loading, here the point of contraflexion is same from the end A and end B. What is the distance of D from the support A? So is equal to what is the distance of B from the support B. You know that is at the point of contraflexion, the bending moment is equal to 0 or bending moment change its sign. So you have to find out the bending moment at a distance x from the support A, and what is the bending moment here you have to find out. Then you have to equate the bending moment to 0. Then you can find out what is the point of contraflexion distance. So for point of contraflexion, here you have to take what is the load is given on the beam, including the end moments. Then after taking the end moments and the external loading, so you have to find out what is the reaction. So here you have to take this reaction, you have to denote the reaction RA dash and RB dash. So here you have to take the end moments and what is the external load is given. Here this is symmetrical, the end moments are also symmetrical, 18.33 kilonewton meter. So here this is the symmetrical loading. So RA dash is equal to RB dash, that is equal to 25 kilonewton. Then after knowing the RA dash and RB dash, then you can find out what is the moment at a distance x from the support A. So the bending moment at a distance x from the end A is equal to mx is equal to RA dash into x minus ma minus w x square by 2. So here mx is equal to 25x minus 18.33 minus 10x square by 2. Then mx is equal to 25x minus 18.33 minus 5x square. Then you know at the point of contraflexion the moment is equal to 0, mx is equal to 0. Then you have to equate the expression to 0. Then after simplifying, so you will get one quadratic equation. So the x is equal to, that is minus b plus or minus root over of b square minus 4ac by 2a. Then after putting the value, then you can find out what is the x distance. So here you got x is equal to 4.1 meter and 0.9 meter. This value is greater than the length of the beam. So here this is, you have to not consider as a point of contraflexion. Only you have to take the point of contraflexion distance. This is 0.9 meter. So here you got the point of contraflexion in the portion AC, that is at a distance 0.9 meter from the end A. Then due to symmetry of loading, the point of contraflexion in the portion BC is also at a distance 0.9 from the end B. So this is the point of contraflexion. Here you got this distance 0.9 meter, and this side also the point of contraflexion distance is 0.9 meter. Then find out the shear force. So here you have to find out what is the shear force at A and what is the shear force at C and what is the shear force at B. So first you take the shear force at B, FB is equal to minus RB dash. So this is the right side upward force, you have to take negative. So shear force at B, that is equal to minus RB dash, that is equal to 25 kilonewton. Then find out what is the shear force just right of C. So when you find out the shear force just right of C, so you have to take what is the reaction at B minus RB dash and what is the UDL present between B and C. So this is equal to 10 into 2, that is minus 25 plus 10 into 2. this is equal to the shear force just right of C, this is equal to minus 5 kilonewton. Minus 5 kilonewton. Shear force just right of side of C, FRC is equal to minus 25 plus 10 into 2, this is equal to minus 5 kilonewton. Then find out the shear force just left side of C. So this is equal to minus 5 plus 10, this is equal to plus 5 kilonewton. So here, so just left side of C, so here there is present one concentrated load at the point C. Here you have to take, this is downward force positive. What is the shear force just right side of C? That plus 10. Then you will get what is the shear force just left side of C. So shear force just left side of C is equal to minus 5 plus 10 is equal to plus 5 kilonewton. Then find out shear force at A. So shear force at A is equal to 5. Then what is the UDL present between A and C? So the UDL present between A and C, this is 10 into 2. So the shear force at A is equal to 25 kilonewton, and that is equal to RA dash. So this is the shear force value at different position. Then after knowing the shear force, you can draw the shear force diagram. The shear force at B is equal to minus 25 kilonewton. Then the shear force just right side of C is equal to minus 5 kilonewton. Then shear force just left side of C is equal to plus 5 kilonewton. Then shear force at A is equal to plus 25 kilonewton. So this is the final shear force diagram, and this is the final bending moment diagram. And you can find out what is the maximum bending moment at the midpoint. So you know what is the free bending moment diagram. What is the maximum free bending moment diagram? This is 30 kilonewton meter. And you know what is the moment, this moment. The moment at the end A and at the end B, that is equal to 18.33. So this is the constant. And here you can find out what is the positive moment at the point C. The positive moment at the point C is equal to the total here, the moment, free bending moment 30, and the fixed BMD here, this is 18.33. The positive moment here 30 kilonewton meter, and the negative moment 18.33 kilonewton meter. You can find out, so what is the moment, maximum positive moment at the C. So this is equal to 30 minus 18.33 is equal to 11.67 kilonewton meter. So this is the final bending moment diagram of the fixed beam. And this 2 point is the point of counterpressure, and here the moment at the end A 18.33 kilonewton meter negative, and at the end B 18.33 kilonewton meter negative. And at the moment at the C, the positive, maximum positive moment is equal to 11.67 kilonewton meter. So this is the final bending moment diagram. And here this is the final shear force diagram. Now all are clear how to solve the fixed beam by moment area method, and then how you have to draw the bending moment diagram and shear force diagram.